All right, so this is number 9 from the optimization packet, and it's a 2-part question. So the first part is a box with a square base, has no top, and is to hold 32 cubic meters. We want to find the dimensions that require the least building material. Okay, so I'm just going to draw a box, or try to. Okay, so the least amount of building material is going to be the surface area. And so I'm going to write an equation for the surface area. And so we don't have a top, so the area of the bottom base is going to be x squared. And then each side of it is going to have an area of xy. And there's 4 different sides, so it'll be plus 4xy. And then our constraints have to do with how much volume the box is supposed to hold. So we want this box to hold 32 cubic meters. So the volume is the base, or the length times width times height, which is going to be x times y, or x squared y, needs to be 32. Okay. And then what I would do is I'm going to just go ahead and solve that for y, because if we solve for x, we'd have to do a square root, and that would just be more difficult than what I want to deal with. Okay, then I'm going to take that, and I'm going to put it in for y in my equation that I want to optimize. Okay, over here, an x will cancel out. So that's going to be x squared plus 128 over x. All right, and then I'm going to find the derivative of that. All right, and then remember, when I'm doing the derivative of a number over x, we change the sign, and then it's going to be that number over x squared. And then if that x had a power, we would multiply by that power and still change the sign and all that. All right, so we want to know when this derivative is equal to 0. So I'll set it equal to 0. And then I'll solve it for x by moving the fraction over, multiplying by x squared, dividing by 2, and then finding the cube root. All right. And then I just want to make sure that this is a minimum. And so I'll do the second derivative real quick. So this is what I was talking about. We are going to multiply by 2. We are going to change the sign, multiply by 2, and then add 1 to the exponent. Okay, so if I put 4 in for my x, it's going to be 2 plus 256 over 64, which is definitely a positive. So that means that 4 is a minimum. And if x is 4, y is going to be 32 divided by 16, which is 2. And that's going to make the dimensions of the box be 4 meters by 4 meters by 2 meters. Okay, and then the second part is a different type of question. So when cut to size, material costs $10 per square meter for the base and $6 per square meter for the sides. What is the cost of the least expensive container? Okay, so this is a different thing. We are this time minimizing cost. So we're going to write a cost equation, which is still the same setup, not necessarily the same box that requires the least amount of material. This is going to be the box that requires the cheapest material. So then we're going to multiply $10 times the area of the base, and then plus $6 times the area of the sides. Now I've already kind of simplified that down when I did this problem up here. This right here is going to represent the area of the sides, because that 4xy was the surface area of the sides, and all I did was take the 32 over x squared and put it in for y, and it reduced down to that. So then it's going to be 6 times that area of the sides. Now, because this is already down to just x's, I can go ahead and find my derivative. Oh, well, that's fine. That's going to be 20x, right? And then if you multiply 6 times 128, that simplifies down to 768x. All right, so then when I do the derivative of that, I'm going to change the sign and put 768 over x squared. Okay, then I want to know when that equals 0. All right, and that's very similar to what we just did. Okay, and then I'll double check by finding the second derivative. So I multiplied 768 by 2. I changed the sign, and then I'm supposed to add 1 to the exponent. Okay, so then if I put in what am I putting in? This decimal, I'm going to get a positive for sure. So we do have a minimum going on here. And then we want to know the cost of the least expensive container. I would take my value for x, and I'm going to put it in for c. Okay, and then I would just do that in the calculator. So 10 times that number squared plus 768 divided by that number. And it looks like you get $341.46 is the least expensive container. So I hope that helps.